Hello, Dr. Huan here. In an algebra class, you have learned logarithmic function and its properties. Today, we will actually go back to revisit, and then we'll begin with the definition, and then we use the definition to derive properties, and then we do the calculus of the logarithmic functions. So first of all, let's define the natural logarithmic function using a integral defined function. So here, natural log of x, that's natural logarithmic function, that's the notation, is defined to be the integral from 1 to x, and the function is 1 over t, and then we integrate t, where this x is greater than 0. So now, if when x is greater than 1, 1 over t, this function is, the graph is like here. When x is greater than 0, the graph is on the first quadrant. And when x is greater than 1, this is just the area bounded by the curve from 1 to this x value. So it's going to be shaded area, right? So therefore, it's the area is greater than 0. When x is 1, so because the upper and lower limits are the same, they're both 1, therefore this integral, which is ln 1, will be equal to 0. When x is less than 1 but greater than 0, then this ln x, which is defined to be this integral, because x is less than 1, let's switch the upper and lower limits, but we have to introduce a negative sign, right? So therefore, we can see that this is the area bounded under the function 1 over t from x to 1. And because this is an area, this is greater than 0 with a negative sign, we know that this ln x, when x is less than 1, will be less than 0. So, by the way, just want to point out quickly, if x is 1, the ln 1 is 0. Therefore, this actually is the x-intercept of this function, right? So therefore, this is the x-intercept, 0, 1. We want to point this out because we'll quickly talk about its shape. So this is how the natural log function is defined. It's defined as using an integral. Now let's take a look at its property. So first of all, domain is 0 to infinity. This is just coming from its definition. Now the range is negative infinity to infinity. In fact, this is when x is approaching 0 from the right, the limit is negative infinity. When x is approaching infinity, the limit is infinity. Well, to give you a little taste on how to prove that, I'll just focus on this one, okay? And the other one is can be proved in a similar way. To prove this one, let's establish one fact. So let's take a look at ln2. What is ln2? ln2, according to the definition, it is the area from 1 to 2 under this function 1 over t and bounded from 1 to 2. Basically, this shaded area. So according to the definition is from 1 to 2, 1 over t dt, right? Now I would like to have you take a look at this little rectangle, this red shaded rectangle. The red shaded rectangle, the height is, the function is 1 over t, so therefore it's going to be 1 over 2. So the area of this rectangle is, the base is 1 times the height is 1 over 2, which is 1/2. And we can see that this blue shaded area is actually larger than the red shaded area. So in other words, natural log of 2, which is the area bounded by the curve from 1 to 2 is actually greater than the red shaded area. So in other words, this is what we know. ln2 is greater than 1/2. That's for sure, right? Now next, let's take a look at this one. ln2 to the power n. There will be a property that we will shortly prove, so that this is equal to n times ln2. Basically, this n can be moved to the front of the ln. Now, because ln2 is greater than 1/2, right? This is greater than 1/2. We can bound this by greater than n times 1/2. Now, basically, you want to look at this. This is greater than n times 1/2, which means n over 2. To establish this result, so this x, okay, this is my x. Do you see that when n is approaching infinity, this also approaching infinity? That's what we want to establish. When x is approaching infinity, we want to show the result is infinity. So therefore, when n is approaching infinity, this x right there, this is my x, 2 to the n is approaching infinity, right? Okay. And do you see that this ln of the infinity is greater than n times 1/2? So we can see that ln of 2 to the n is greater than 1/2 of n. And this n is infinity, approaching infinity. So therefore, this is infinity, right? This is infinity. And therefore, we prove this. So this guy is greater than infinity. That means itself is approaching infinity. So this is how we prove this result. There are some other ways to do that, but this is one way to do it. To prove this one is very much alike, you can establish the following. So I'm going to give you a little quick hint. So you can show that ln 2 to the negative n is less than negative n over 2. So try to establish this one. And when n is approaching infinity, okay, 2 to the negative infinity is approaching 0 but positive. So that's what you want. You want this x to approach 0 but from the right, which means positive, right? So in other words, when n is approaching infinity, that's what's happening. And when n is approaching infinity, this is negative infinity. So therefore, this ln of a value approaching 0 from the right will be less than negative infinity. That means itself is negative infinity. So that's the little hint on why the range is negative infinity to infinity. It's not that it's not trivial. It takes a little nice proof. So let's back into the property. Continue on the second one. The function is continuous. This is really just coming from because according to the fundamental theorem of calculus, right? The derivative of this is just 1 over x. So that means it's differentiable. Because it's differentiable, it is continuous. Okay. So this is really coming from it's differentiable. So therefore, it's continuous. Okay. And also, if you look at the derivative of this function, so the derivative, what is the derivative? F prime of x is 1 over x, according to the fundamental theorem of calculus again, right? And it's definitely greater than 0 because x is greater than 0. Therefore, this is greater than 0. Therefore, it is increasing and is strictly increasing and therefore 1 to 1. The last fact that we can see from the second derivative of the function. So this is the first derivative, right? The second derivative, f double prime of x, is equal to negative 1 over x squared. The derivative of 1 over x is negative 1 over x squared using the power rule. And because this is going to be less than 0, So therefore, we know it's concave down. So I believe at this point in time, we actually can use all the information that we derived to make a graph of the log function, okay? So first of all, the domain is from 0 to infinity, so we will have the graph on this side, and the x-intercept is 0, 1, so 0, 1, this is the x-intercept. We also know that it has to be strictly increasing, right? Strictly increasing, so strictly increasing, and it also bends down. So therefore, the only possible curve is like that, right? So therefore, it will look like that. Will look like that. Okay. Of course, without plotting points, it's hard to see the exact shape. But for now, this is the general shape. Okay. This side going to infinity. This side going down to negative infinity. All right, so that's the some basic properties of natural log, and now let's look at a few more logarithmic properties. The first one, assuming a and b are positive numbers and n is rational, and here we have the four properties. The first, by the way, actually going through the proof of these four properties will help you understand the definition much better, much deeper. The first one is ln1 is equal to 0. Well, this is actually a fact, right? We already see that when this is 1, when x is 1, because the lower and upper limit is just the same, so therefore the integral has to be 0. So therefore this is pretty trivial just from definition. And the second property is ln of the product of AB is equal to the sum of ln A and ln B. This again, direct and indirect proof of this property. Let's take a look at one of the approach. So here I'm going to start with the left-hand side, okay, left-hand side, ln of AB. According to the definition again, please pause the video. If you want to give a try, write down the definition for ln of AB. So here's the definition. The lower limit is 1. The upper limit is AB. And we're going to integrate the function being integrated is 1 over t. So this is according to the definition. One of the integral property is, we call it additive property. So we can break it into the two parts. So the first one is the integral from 1 to a, 1 over t dt, plus the second one is a to ab, right? 1 over t dt. This one is actually LNA, so we have that established. We just want to show that this is actually LNB, then we are done. So in order for us to show the second one, we have to, again, the only tool that we have is the definition, and the definition requires the lower limits to be 1. So therefore, we have to do something so that this becomes 1. So substitution is what it takes. So here's the trick that how to do the substitution. Let u be, okay, t divided by a. How is that come up? Because after you do the substitution, we have to change the limits as well, right? So when t is a, we want the new integral to be 1, so t divided by a, okay? So that's some thought, hint to come up with this substitution. And because of that, let's say when t is equal to a, right, your u is 1. When t is equal to ab, what is your u? U is ab divided by a, which is the b. So u is b. So we now have the, so the first integral, just copy it down. The second integral is the limits will be from 1 to b now. Let's continue to do the substitution here. So 1 over t, we have to, from u equals t over a, that means t is u a, right? Or a times u. And dt will be a times du. So that means here we have 1 over ua, and dt will be a times du, and we cancel the a, and therefore we actually now have it. This according to the definition, which is ln a. And this one, this is a dummy variable. You can just think of it as 1 over t dt, right? So according to the definition, this is ln b. This is ln b, which is the right hand side. So this is how then we've proved the second property, right? Now let's look at the next one, the number 3. Actually, once you have the number 2, the number 4 follows immediately. But let's do it in order. Let's take a look at number 3. So number 3, again, the only tool that we have now is just the definition. So the left-hand side, according to the definition, will be the integral from 1 to, pause the video if needed, okay? So if you want to give a try using the definition, pause the video. So the upper limit will be a to the n, because that's your x, right? That's the x there. And 1 over t dt. And if you look at the right hand side, this ln a, according to the definition, it is from 1 to a, 1 over t dt. So therefore you do want to do a little substitution so that this do something so that this becomes the a after the substitution. So here's the so again, strongly recommend you to pause the video, think about how you would do this substitution. So actually let t be u to the n, okay? T be u to the n, or you can think of u as nth root of t. Either way. Now, so let's take a look at the lower and upper limits here. Let me zoom in a little. We can see that when t is 1, okay? When t is 1, and what is the u value? Like 1 is what raised to power n? What raised to power n? Don't you think it's going to be 1, right? So therefore the lower limit is 1. And then when t is a to the n, okay? So when t is a to the n, so what is u has to be? And just by matching, we know that u has to be equal to a, right? So when t is a to the n and t is equal to u to the n, so we need to figure out that u. So basically, it's just by matching, we can see that quickly. So therefore, this is the upper limit is going to be a. And 1 over t, okay? T is u to the n. And the dt, we need to figure out the dt because t is equal to u to the n. So dt, apply the power rule, it's going to be n times u to the n minus 1 du, right? So here the dt is actually n times u to the n minus 1 du. And we have some cancellation. So when you cancel that, you're left with u here. And n is just a constant, so you can pull the constant out of the integral. So you're left with the integral from 1 to a, 1 over u du, which is the ln a, which is the right-hand side. Okay, so this is how we prove the property number 3 actually. property number 4. So property number 4, the trick is, let's start with LNA. The LNA can be considered as, so here's the trick, B times A over B, right? B times A over B. And now we can apply the previous established result. When you have product in the Ln, it becomes the sum of the individual log. So therefore, we have a product right there, this guy times this guy. So it is equal to Lnb plus Ln A over B by the second property. And therefore, you can see that Ln A over B is equal to, just solve for that, Ln A minus Ln B. All right, so we have established 4 properties, and now let's actually apply them, okay? So before we do that, so let's take a look at when you have products, that becomes the sum. When you have quotients, that becomes the difference. So basically, the B, when it's in the denominator, then it becomes the negative, okay? There's a negative sign in front of it. So now let's apply the logarithm properties and expand the following logarithmic expressions. So first of all, we see a quotient of the two. So therefore we have ln 5a cubed b minus ln c, square root of c. A square root of c can be viewed as c to the power 1/2. And then this is according to the property number 4, right? Property number 4 right there. And then now we can use the property number 2, the product becomes the sum. So we have ln 5 plus ln a cubed plus ln b, and then minus ln c to the 1/2. So lastly, let's take care of these exponents for this for the exponents, which is using the property number 3. The exponents can be moved to the front of the log, right? So therefore, this is equal to ln 5 plus 3 times ln a plus ln b minus 1/2 ln c. So this is the expanded version of this condensed version. Actually, if you observe that quickly, you can do it faster. To do some observation here, okay? So when I see the terms in the numerator, they are gonna have the plus sign, okay? Plus sign. The term from the denominator, they will have the negative sign. And also, these exponents can be quickly moved to the front, so you can actually like condense the step 2 and step 3 into one step once you are comfortable with it. In this example, we want to condense this expression into one single log expression. So from previous experience, we know that when this is negative, and we know this term will be in the denominator, right? And when this is positive, we know this will be in the numerator. And of course, we will move these two to the, make these two become exponents of this x plus 2. And similarly, the last one, when this is negative, this term will be in the denominator, and again this 1/2 will become its exponents. So therefore, with that, we can actually quickly do this one. So what's in the numerator? The one with positive sign. So it's going to be x plus 2 squared in this case. And this one will be in the denominator because of the negative sign. So it will be x. And the next one, 1/2, becomes the exponents, which is the square root. And because of the negative sign, it will be in the denominator. Alright, so this is the first video that covers the the definition and the derivation of several properties. Actually, let's quickly read through a comment right here. So when using the properties of the logarithm to rewrite logarithmic functions, check to see whether the domain of written function is the same as the domain of the original. For instance, ln x squared is actually not the same as 2 ln x, because this function being x squared, it will never be negative. The domain will be everything but 0. But this function, ln x is the domain is 0 to infinity. They are not they do not have the same domain. Therefore, these two are considered different functions. Even though you may think move the 2 to the front, that will change the function. Okay, so please be aware of that.